Morning. We continue today on our CT journey. Today might seem like a lot of review from the last lecture, but I think the concepts that we're trying to learn in these 3 lectures or so are sort of the central concepts for computed tomography. So we're going to review a few things. There's some other very good books on computed tomography out there, and a classic one is Keck and Slaney. That's been around since the 80s. And so most of the 250 people in the world who really know what CT is all about have learned CT through Keck and Slaney. And then there's, this is a very highly specialized book, very mathematical and very explicit definition of many things in CT scanning. It's a great book. So if you go into a graduate program where you're doing imaging and you're going to do CT, this is a book you really want to have. This is a lot more conversational than this book, and it has sort of terrific insights into CT. Okay, were there any questions after last week that you want to review quickly, or? Okay, let's just get started then. We're gonna start back here. Oh, say again? I have a question about the project. Oh, okay, question about the project, shoot.
Do we just need to get our topic okay, or do we still need to submit like that 1-page document that's on the description?
You want to get it okay from me, especially if it's not one of those questions there that were pre-written. And ideally, yeah, just it doesn't have to be a whole page, it can be a half a page, but just an idea of what it is you're going to address, so that we all know that we're on the right track, right? It doesn't have to be terribly formalized and everything. And recall that the project itself can be quite sophisticated if you want to compute something that's sophisticated. However, the presentation has to fit into 9 minutes plus 3 minutes of questions. And so when you bring your slides up, you should have, say, 8 to 10 slides somewhere in there, right? Not 26, because you're not going to make it under the 9 minutes, right? So the general rule for giving talks, technical talks, is 1 slide per minute. That seems slow, but it zips right on by. So it's a good rule to carry with you. Okay, we're gonna keep going on CT reconstruction. And this is a review from last lecture. Recall this capital G of K theta is the God-given Fourier transform, right, of our projection data in polar coordinates in Fourier space. And as we'll see in MR, we normally label these coordinates as K sub X and K sub Y. These are spatial frequencies, or cycles per millimeter. And one suggestion, obviously, for creating an inversion such that we can get back to our map of mu x, y, was create these line samples through the Fourier transform of our object, and perhaps interpolate them onto a rectilinear grid, and then just do a fast Fourier transform, and then we have the inverted solution. Well, you'll notice, though, that when you go to put all of these radial samples onto the rectilinear grid, you'll have many more samples towards the middle than you do out towards the edges. And hence, that's a hint that we're probably going to have to weight the samples, the individual samples in the middle, weight them down in order to recover a reasonable estimate of the Fourier transform. So when we say interpolate this point in Fourier space, we're going to have many, many samples around it, right, to estimate its value. And so those samples will have to be weighted accordingly. Whereas out here, we'll have fewer samples because the ray will be farther away at this point. algebraically, it works out as a very nice way to explain where convolution back projection or filtered back projection comes from when you write down the inverse Fourier transform of this capital G K theta. Remember, we derived this by taking Fourier transforms of the projections, right? And this, again, it is the absolute continuous God-given Fourier transform of our image, which is the attenuation coefficient as a function of position in space. Okay, so mu xy is the image we're after. Every position in the patient xy, we want to find out what the attenuation coefficient, linear attenuation coefficient is there. And one way of doing that is to take the inverse Fourier transform of this function. In order to do that in polar coordinates, we write down the Fourier transform in polar coordinates with the appropriate Jacobian. And that is the area element for this integral is dk in the k direction, and then it's k d theta in the theta direction. And you have to weight it by k as you go out, right? Because these elements get larger as they go out radially. And we can put the theta dependence of this, we can pile that up into this L variable here, where L equals x cos theta, y sine theta. Remember, x and y for this integral are just fixed numbers because they're the position that we're estimating. And rewrite this integral such that it looks like this, and then do the integration with respect to the k direction first. And that turns out just to be the Fourier transform in the k direction of this object, which is k times the Fourier transform of the image. Yeah?
So for the first line up there, the fact that it has the Jacobian, that's why it's not just purely a reverse Fourier transform. That's why
this is the inverse Fourier transform, and when you do it in polar coordinates, you need that Jacobian. And so this gives us a hint as to why filtered back projection works and non-filtered back projection does not, because if you take this out, you get this hazy picture, right? And so this is just the inverse Fourier transform. It turns out also to be the filtered back projection of our image. So the Fourier transform of this object, or the inverse Fourier transform of this here, we're going to call G star L theta. So now we have spatial coordinates L. We have one for each theta direction. And then this integral is simply the back projection of these objects. It's just for each theta, we're just going to add them up, right? And when we look at the expression in terms of the convolution theorem, we have the inverse Fourier transform with respect to k here. And this is our original GL theta that we measured on our detector, convolved with the inverse Fourier transform of a ramp, right, or k. And so that is equivalent to this inverse Fourier transform, this convolution, by the convolution theorem. And then the filtered back projection, these G star L theta, can be just considered your projection or your data convolved with this function, right? Which is the inverse Fourier transform of the ramp. So let's take a look at a pictorial representation of this. First in Fourier space, where we have a projection. This is our G, right? First, this is the L direction, and this is for a specific theta. We look at its Fourier transform, or we get its Fourier transform in Fourier space. We can multiply that by absolute value of k, which is this ramp, right? And then we take the inverse Fourier transform of that, right? Which gives us the filtered or convolved back projection once we're back into space. This is in frequency space, and then back project those. If doing it in space throughout the whole process, as opposed to going into Fourier space, we can take our projection GL theta, which is our data, right, for each theta, convolve that with the inverse Fourier transform of the ramp, which is a function that looks like this, right? And then generate these G star L thetas after each one of those convolutions. We get a G star L theta, back project those, right? And that will give us the same thing. And so here it is pictorially with GL theta. This is what we measured in our detector. This is L for one specific theta. And then when we take this function and we convolve it with the inverse Fourier transform of the ramp, right, that wiggly function, this is what comes out. And these are the functions that we want to back project to make our image. And we'll do a little demonstration here of what that looks like. So, let's move here. So here's GL theta of our favorite function to play around with, which is the rect function, right? And we're going to see what the back projection is of this. We'll see what the image is as it evolves of a square. And these are what the GL thetas look like of a square as they're back projected from different angles, right? And then as we build those up through back projection, we get this picture. Okay, so this is without the convolution. This is without multiplying by the ramp. Okay, so as we go to different angles, so here's 45 degrees. Well, we can get it right at the peak there. Through a square function in the plane, we'd have a peak in the middle and it rolls off to the edges. We project that back here, and then as we go on and project more and more, we see the object emerge, but it has these very blurry edges, right? Now we look at the G star L theta functions, and this is after convolution with the inverse Fourier transform of the ramp. This is what it looks like. Much different looking function than the original one. And as these change their angle, you can see that the changes in the features of the projections, and they add up to give you the accurate estimate of the underlying object with the sharp edges intact. Right? So you can see that when we project at different angles, so if we're purely projecting vertically now through this square, we're going to get extremely sharp edges here, right? Because we don't have any angle, there's no integration over partial amounts of this square. We have space, and then we have part of a full integral through the entire dimension of the square. So we basically have a step function or a rect function. And then after the convolution, it turns into this function, which you can see is really emphasizing the edges of this object for this view, this particular view. That's because we've got a perfectly straight object and we've got perfectly straight projections here. So it's going to be a pure rect function. Convolve that, you get this thing. And you can see all of your resolution about that edge is coming from this projection, basically, right? Because when we tilt the angle, you're now tilted towards the edge. And so you start getting projections away from that specific edge. One of the things that can happen is that if your square is actually tilted slightly, such that no projection is actually parallel to the sides of that square, then you have an interesting situation, right? You never get an absolute sample of that edge. It's always between angles. And so that's one of the losses of spatial resolution in CT, is that unless you get enough angles, to sample that edge, you're going to get blurring on that edge. Right? And so we'll watch that one more time. You can see the edges just sort of snap into focus as you pass through that particular angle. Right? So this is the ramp filter, it's called, because in the Fourier space, it looks like a band pass filter. It certainly is not a low pass filter because the low frequencies are completely attenuated at 0, right? But when you do back projection, you will get enough integral in the patch around 0 that you will get DC in your image. And the Fourier transform of this function looks like this. There are many ways to try and smooth out this function so that you don't have this essentially huge abrupt change in both the value of the function and the derivatives of the function. You know, it's going to be badly behaved at certain parts when you have these frequencies amplified to such a degree. Yeah.
So the ones on the left are regular and the ones on the right are in Fourier space?
Yes, this is the filter in Fourier space on the left. So this is the ramp function in Fourier space. And remember, it comes from the fact that we have that Jacobian, which is the absolute value of k, and that's what this looks like. This is just going up as k, right? And then when you look at what that function looks like in space, take the inverse Fourier transform of this thing, it looks like this in space.
One on the left are in Fourier. And one on the right.
Exactly. Fourier space, and this is in space with millimeters. Right? So you're susceptible to a couple of things: noise amplification and artifacts off of discrete edges when you have this remarkable amplification of the high frequency data versus the rest of the data. And so a number of filters are used to smooth that down. This is one shape is a cosine filter. Instead of using a ramp, you plug in a quarter of a cosine there, and that will roll it off as you go towards the higher frequencies. It'll tamp down the higher frequencies. Here's the Shep-Logan filter, and I've forgotten the formula for Shep-Logan. Sorry, we can look that up. Looks like we have a full cosine cycle here, right? So now we not only ramp it down, we take it down to 0 at the maximum frequency. And so that's going to smooth things out a lot. And you can see in space, the convolution kernel, when you're doing convolution back projection, this is the function that you're convolving your data with, your GL theta. Each one of those gets convolved with this. It gets broader, and the side lobes get broader, and they don't ring out as far. Right? So it's going to give you a blurrier picture, basically. And then a Hamming and a Hanning window. And it looks like that. Hamming looks like the Hanning, except you don't go down to 0. Here, you not only do a full cosine cycle, you get to the point where you have a 0 derivative, right? So it's sliding in, it's a 0 derivative. And so this is a highly smoothing filter. And I put 2 MATLAB scripts in the modules. And one of them, you can just look at the effects of these different kernels, because in MATLAB, the radon and the iRadon function, you can just pick these different kernels. And so you can take a look and see what they do to both the background noise and the very small featured object, say a little 1 pixel image, like a bright pixel. We can take a look at it quickly. And this is review. Here's the Romlock filter, the ramp filter. This is the Hanning, and that's the difference between the images that you would obtain. you know, when the convolution is done, it's done as a discrete convolution. And so these filters are sampled to these particular values on this grid. And then that is the convolution done. So the kernel for the convolution, i.e. the number of numbers you have to carry around to do this convolution, is quite small. And it's a local convolution. Here you've got about 10 numbers you need to know, and you just run that across your GL theta. And that can be done very fast. Again, just pictures of what happens to a rect function when we convolve it with those discrete kernels. For the full ramp, we get these really high edge amplifications, and they reduce as we broaden that filter. So are there any questions about that? Any general questions? Okay, great. Let's take a look at what happens when things go wrong. And sometimes it's illustrative of, you know, the process itself. Here is a single projection of this image, which is a disk, right? So these are just integrals down through the disk, and GL theta will basically be independent of theta if this thing's at the center of the scanner. And I'm just gonna get a set of these. When we take the filter, or we convolve this with the Romlock filter, the inverse Fourier transform K, we get this. This is the first example we saw. We now have a nice flat top and edge amplification. If, for example, in one view, say we did 800 views, 800 theta values, and in one of those views, some electronic noise happening. There was a blip on the line or something, and you got some noise that popped in on a couple of detectors. And here we have a 10% change in amplitude on those detectors, right, for this particular view. The issue is, because this is very high frequency, when you do the convolution and you amplify the higher frequencies in your signal, this error tends to become a much higher percentage of the signal, right? And so now we're looking at this as the function that we're going to back project. And what shows up are these streaks in your picture. So if it happened only at one view, you know which view it is, because here are the streaks, right? Those of you who are keeping up entirely would say, well, wait a minute, it's one view. Didn't you get a fan beam of views there? Shouldn't it like fan out like a fan beam? And that is true. The only way you'd get parallel streaks from a fan beam is if you had the noise happen when specific views hit the same angle, right? But anyway, for most of what we do mathematically, we assume that we have parallel beams and they all occur at the same time. In a modern scanner, that's usually not the case. So these are streak artifacts from electronic noise in a detector at a single projection. You can get the same type of noise if there's, for whatever reason, there's a lag or a lull in the gain at a specific angle. It gets, amplified by the convolution, and then you get a dark streak through there. Now, this is a really interesting one. This is the raw data, GL theta, and upon this raw data is a 1% error in one detector. Right? So if this is 100, it's off by 1, which is about the width of this line. Right? So when you do the convolution, it pops up as a small error. Right? However, if it's a constant error and it happens on every angle, right? So for whatever reason, the gain of this detector, remember your detector elements lie along here, And the gain of this detector, for whatever reason, is either low or high. And it's different than when you calibrated it. Then you would get this small change in signal, but it would be there for every view. And then you get a classic ring artifact because it's there for every view. It looks like there's a ring object in your scanner that is producing this signal. Right? And so these, actually, when you get down to very low photon counts and you're challenging a system and its signal to noise, oftentimes you'll see these rings because you need to be within a few percent of the true gain. And so it's a classic looking artifact. The way you get rid of it is you measure where that ring artifact is, you go back to your raw data and you throw that point out. And you just interpolate the neighboring points across. You say, okay, that's not in my object, that's a artifact. Therefore, I'm going to throw the data out or modify the data in some way such that it's smooth. So we can look in the book, there's a section on both looking at the resolution of this type of imaging and looking at the fundamental signal to noise and what the signal to noise is dependent upon. What things that you can change on the scanner, dials that you can change, and how does it change signal to noise. And if this is our estimate of the underlying image that we're trying to achieve, and remember, this is in Prince and Link's notation, ours is usually mu xy. This is our estimate. The function, as we're doing the Fourier transform, gets multiplied by all of these, which are essentially filters. We can go through them one at a time. This one we know about because we just talked a lot about it. It's the Romlock or the ramp filter. All right, so that's going to increase the weighting as a function of spatial frequencies. This is the windowing. And we just saw a list of those possible windows. One was a Hamming, one was a cosine, one was a cosine 2, etc. And so that, depending on the windowing you select, you will blur the picture, right? Compared to having no windowing and just the ramp filter. And then there's a fundamental blurring that occurs, which is proportional to the width of the detector element. So when we're sampling our rays, we're not really doing point samples of our object. We have a width of a detector and it's integrating over that width to count up the number of photons that go into that bin, that detector bin. And so it has a size, right? And it's usually, on modern scanners, it's about 1 millimeter. So usually 1 millimeter by 1 millimeter of these detector elements. So if I can have 1,000 of them, a meter's worth of them. Each one's separated by 1 millimeter. Ideally, there's no wasted space, and over that entire millimeter, you can integrate all the photons that hit the detector. Right? And so now we have, what is it? It's a rect function, right? It's a rectangle. We've integrated everything inside that rectangle. So in Fourier space, it's a sinc function. And so it blurs the true underlying object. And that blurring can be captured by just multiplying the Fourier transform of the true object by the central part of the sinc function. Right? So if I have a 1 millimeter width detector and I look at the sinc function, right, the first 0, right, where it occurs in that sinc function as we go down, is the point at which we would have 1 full cycle inside that 1 millimeter, right? So 2 cycles per millimeter. We know with our system we can't image that, obviously, because we have, if there's a full cycle inside one detector, it's going to integrate to 0, right? So that's where the 0 of the sinc function is for that rectangle in Fourier space. and this is where the Nyquist criteria comes in, we can image to half that, which is one detector is up, the next detector is down, the next detector is up, the next detector is down. That frequency is 1/2 cycle per detector element. Right? And so at that point, the sync function in Fourier space has come down in its central part to about 70% of its peak value. And so that low pass filter is applied to the Fourier transform of the object in order to model that blurring. Right? Oh, there's one missing thing here, which they didn't put in the book for this formula, which is the X-ray spot size. And as you can imagine, the true source of the photons is not an infinitesimal spot. It's not a point. Right? If it was a point, we would cast an absolutely clean shadow and we wouldn't have to worry about the spot. However, it's usually a rectangle and it's usually about 0.5 millimeters on a side, that rectangle. That is the space on our X-ray source that is producing the X-rays. So that spot size also adds an additional blur to the picture, right? And you can model that by just convolving with the size of that spot. So going back to our image quality concepts, we have an ideal image of a tiny little thing we would put in the scanner, and we would get a peak where that thing is and nothing anywhere around it. If the object has this diameter, for example, and our system has this intrinsic resolution, then this is called our point spread function. Right? So we have a little metallic bead. I want to take a picture of it, and this is the image that comes out of my scanner, right? And that's called the point spread function of the scanner. So it tells you spatially what a point object looks like. If I have different point spread functions, I can also characterize them with what's called a modulation transfer function, which is the equivalent information in the Fourier domain. So this is space. And so when I ask, well, what is my size of my blob that is the point spread function, I could give you the actual spatial dimension at the half height of this function. And that would be in millimeters. I would say, well, my full width at half max is 1.2 millimeters. And that tells you, if you know what this function is analytically, then it tells you everything you need to know about the point spread function. In the Fourier space, the Fourier transform of this object is called the modulation transfer function. And this is in line pairs per millimeter or cycles per millimeter, cycles per centimeter. It's a spatial frequency. And it shows how, as you get to higher and higher frequencies, the modulation of those frequencies, the ability of those frequencies to pass through the system decreases, right? So at this frequency, I would only get 50% of the amplitude that I would with a frequency that is lower over here. Remember, this is a review of a diagram where I have 3 different sine waves going into this system. Each one starts out with the same amplitude. All right, we can think of it as these objects, right? They all start out with this same amplitude. If I had very high spatial frequency or an MTF that permits high spatial frequencies or a point spread function that is very, very narrow, then I would see a picture like this. With an MTF that cuts off high spatial frequencies, what happens is this spatial frequency passes with very little attenuation. This one passes with approximately 50% attenuation of the amplitude, and this one only 13% gets through. So this is what comes through, and this is the result. Right? You get a blurred picture. You can still sample this frequency, but by the time you get down here, it's pretty well gone. Right? the height of those amplitudes, or the reduction of those amplitudes, is the modulation transfer function, right? And if you want to measure it in CT, one of the things you can do is build a phantom. A phantom is just an inanimate object, like a plastic thing, plastic and water or whatever, and you put it in the scanner and you image it and see what it looks like. You know what it looks like, but you want to see what the scanner makes it look like. So this object has, at a specific radius, if I draw a line through here, it has different cycles per centimeter, right? And the frequency of the wave gets higher as I go around the clock here. And so you can just look at the object and measure a profile through there, and then just see where does it fall off. And then that map will be the measured modulation transfer function of your system. And for instance, this came out of a paper where the authors claimed that their way of manipulating the raw data preserved spatial frequencies that standard filtered back projection did not. And they demonstrated that by saying, look, our amplitude here of this wave is higher than it is with standard filtered back projection. So you can quantitatively look at the two MTFs and say which one is passing higher frequencies. And we're in the lab, we're interested in measuring little pieces of calcium, like high detailed objects in coronary arteries. And this is a human heart with a right coronary artery here, and the lumen is here, and this is a piece of calcium. And this is imaged with that heart in a jar. It came from a person that's now in a jar, so that it's perfectly still and we can image with as much radiation as we like, etc. But it still has the same physiology as a coronary. And take a look at how the scanner can visualize that piece of calcium. It's a very bright signal, right? It's very localized. This is the wall of the right coronary artery. It's not very large. That's the lumen, and there's the piece of calcium. This is the difference between the small spot size on the scanner and the big spot size. If a person gets large and you need to get more X-rays through them in order to sample anything, you have to use the bigger spot size to just generate more X-rays, right? More MA. And so when you change that setting, you go from this picture to this picture, right? The only thing that changed here, this same MA or same number of photons is being used. It's just this was produced with a small spot size, this was produced with large, and that's the difference when you zoom in. So you can see this signal is focused more tightly than this. There's a blurring here. This goes back to the introductory lecture to CT, and this is a desktop CT or a lab CT that a colleague of mine has at Hopkins. Here's his X-ray tube. This is the object, and this is his detector. And he can make images down to with pixel dimensions of about 150 microns, right? So 0.15 millimeters. And so we gave him the heart, and he put it here, right? So, okay, now you image this heart so we can see what's there. And these are the images that he obtained on his system. And when we zoom in, this is on the clinical system. When we zoom into this vessel here, you can see a beautiful depiction of the shape and size of that piece of calcium and the lumen and the vessel wall, giving an underlying truth of, here's the underlying truth. This is the vessel, lumen thing, and that's what the clinical system is going to do. So, you know, it's a way of testing, you know, do you have sufficient resolution to detect these objects? On our system across the street, we can easily, this little white dot here is a I think it's 150 micron piece of tungsten wire that goes through in water. And so it produces a very small dot. I mean, it's much, much smaller than a pixel, for example. This is what an image of that thing looks like when you do the standard recon filter, which is probably like a cosine filter, something like that. So it's not a ramp filter, it's pushing the high frequencies down. It's like that cosine filter we saw. That's what it looks like. And this is what it looks like when you just use the ramp filter. You don't use any of these Hamming or cosine or anything. You just say, we just want the highest resolution possible. Let's use the ramp filter and the torpedoes. And you can see the noise amplification is pretty significant, right? However, the amplification of the actual peak value of the signal is also pretty significant. So if we plot a profile through these two objects, this is a profile through the standard filter. The peak gets up to 500 Hounsfield units. This peak gets up to 1300 Hounsfield units. This is with the ramp. But you can also see the variation in the background here is plus or minus, I don't know, 200. And here it's plus or minus 50, something like that. So the background settles down when you use the ramp filter because you average out the noise, just as we saw in the picture. Right? If you're trying to approximate just on the back of the envelope, what is the point spread function from a cascade of different things? This is a very useful formula in that if each thing can be modeled as a linear shift invariant system and each point spread function is like a Gaussian blob, then the full width half max of all of those cascaded systems is this formula. You take the full width half max of each blur, progressive blur, square it, and then take the square root of the whole thing. Okay, so if we had a system that, for example, had a full width half max of 2 millimeter without detector blur, let's say that gives a full width of half max of 1 millimeter, right? When I put both of those together, I get a full width of half max of 2.2, right? So you convolve this larger, blurrier thing with a smaller thing, but it still broadens it to some extent. And in looking at signal to noise and just measuring it in images, as we saw before, this is review. You have an observation and its mean, and then the noise around that observation is the statistical variation of the pixels. And one way of doing it is if I take 1,000 images and I look at one pixel, one position in the patient, and ask, what is the variation of the pixel value in those 1,000 instances of that process? And that, if you plotted a histogram of those, you could get this sigma. If the system is ergodic, you can also just draw a box in the background and measure this sigma. Just take 1,000 pixels in the background and say, the statistics of taking 1,000 pixels in the background is the same as taking 1,000 instances and measuring 1 pixel. Right? And so these are classic formula for modeling the mean and standard deviation of the background. Most of the time, when you do the statistics on what you're measuring, these functions do the trick. In X-rays, it turns out that the process itself of actually creating the X-ray photons is a Poisson process or a Poisson distribution. So when you get down to low photon numbers, you need to take into account that the actual probability of getting a photon goes as a Poisson distribution. Once you're above about 10 or 12 or 15 photons, something like that, you can model it as a normal distribution. The two distributions merge and become the same thing. But down at the low values, you need to model the noise as a Poisson distribution. That's one of the differences between CT and X-ray versus MR, right? Is that here you're counting photons. And so when you get down to low numbers of counts, you have to take into account that it's Poisson distributed. And here's just a simple way of measuring what contrast to noise is. You have a mean in the background. You assume that the random values around that mean, right, are the same random value you would get if you took 1,000 of these pictures and took that root mean square deviation. And here's our target. We have a mean value of the target and we have a standard deviation at the target level. Most of the time, if you're writing down some kind of theoretical explanation of what the signal's noise is going to be, you're going to assume that the difference between the target and the background is small enough that the statistics for measuring sigma in both those places will be the same, right? If this object has an extraordinarily different value than the background, like it's metal or bone or something like that, then this kind of falls apart. You know, you really have to understand what the variance or the variation of the signal is in that particular object. It will be different than it is in the background. The other thing you learn really quickly, practically speaking, when you do CT is that you can measure and make all these wonderful images when you put an object and the background is air. So if I take a little toy or something and I put it in the scanner, it can be a tiny little thing. I can measure it very accurately. Or, for example, when you tape a phantom down with, say, just Scotch tape, right? Scotch tape's pretty thin, right? And you tape it down like this, you will image the Scotch tape in air, and you'll get a really nice clean signal for the Scotch tape. And that's a really thin object, right? That doesn't work out when you're in water, right? So when you have a background of water, many more X-rays are getting absorbed. And so the difference between your signal is starting to get much, much lower, and the Scotch tape goes away, unfortunately. But in air, there'll be a view where you're just going straight along the Scotch tape or close to it, and you'll see the darn thing. So when you first get in this field, you start doing all these experiments in air, and you think, oh, this one is wonderful. And then all of the people who have long-term experience say, nah, you have to do everything you want in water or inside a ring that basically simulates the amount of attenuation a person would achieve. So if I have a phantom that is looking at a coronary artery and I want to image the resolution, I need to put that inside a phantom that is like a person's torso, right, in order to get anything reasonable. We'll just quickly go through this. We're just going to get down to this formula where all the meat of this is. But if you're into this kind of derivation, Jerry does a pretty good job of making a set of assumptions such that he can write down an equation that gives you, to the first order accuracy, what the variation is in the mu value of your picture. So if I get a mu value and I want to know what's the standard deviation around my estimate of that mu value, what is it dependent on? Well, we know a few things right off the top of our head, right? We know it's going to be dependent on how many X-rays we use. If I use a lot of X-rays, I'm going to get a very accurate value of mu. So the value divided by the variance is going to be high. I'll get a good contrast to noise or signal to noise. We also know a couple of things, like through common sense, we would imagine that if I took an image and I did 400 projections and I made a picture and I got a contrast to noise, and then I did exactly the same thing, but I took 800 projections. I filled in spaces between each projection. My contrast to noise it gets better. Right? I just have more estimates going into that average, right? And so here, in deriving these dependencies, he writes down the discretized version of the estimate of mu xy. And so this is essentially convolution back projection in its discrete form, its digital form, right? Where this takes care of the ramp, right? And puts us on a line projection. These are our data for each width of a detector. It has a width of t, and each I is a different data point along the detector. So IT is kind of L, the distance along the detector, right? And then J is just the number of projections we have. So it just enumerates projections. So if we took 400 projections, N would be 400, right? And I'd have 400 of these things. When you do this and say, okay, that's going to be my estimate of mu xy, this comes out in the wash as being what the variance is going to be dependent on, the noise is going to be dependent on. He makes the approximation that, as we said, that everything is about the same level. The number of counts are about at the same level. And a couple of things are pretty obvious. The variance goes down as 1 over the number of projections, right? So if I double the number of projections, then the variance goes down by a factor of 2, right? So that seems to make sense. Let me see if the other mic works. All right. If we turn up the current on the X-ray tube such that we just get more photons, the only thing we change is the number of photons, right? So just crank up my MA, produce more photons, then the variance goes as 1 over the number of photons. So if I double the number of photons I'm detecting, then my variance goes down by factor 2. Okay. The interesting thing here is if I change the width, this is like photons per unit width. T, remember, is the width of the detector. And so it's like number of photons per detector. Okay. So if I change T, all I do is say, well, I'm going to make my detector elements twice as wide. Okay. What happens is the number of photons at that point goes up by a factor of 2, because we just detect twice as many, and nothing happens to the variance, which is kind of interesting, right? In that it's saying you can always rebin your data, right, to get back to a point where you have enough photons to do something sensible, right? So if my T is really small and I'm not getting enough photons, I can always just open it up, take every 2 detectors and add that signal together. And so my number of photons will get to a level that it's reasonable, right? Sigma doesn't change, signals noise doesn't really, fundamental signals noise doesn't change. However, the resolution will change, right? Because now the T is wider. The sinc function we're multiplying by in Fourier space, it's narrower, and so we attenuate stuff. Okay, so those are the big things. This is a parameter that governs the width of the filter in Fourier space. And this is why having a ramp function, like this is a ramp function, having it go out to higher frequencies really cranks up the noise, right? Because it goes as the cutoff frequency, like the cutoff of the ramp to the cube, right? And so if I, double that, if I have my ramp like this and I say, oh, you know what, let's just open it up so the ramp goes farther up and I admit all of that stuff, then my variance goes up by a factor of 8. So the noise just goes up really high as you increase the width of the rect of that ramp filter, right? And you can kind of think of that as it increases the total volume as we go around underneath. It's like there's a cone missing from the center of Fourier space, right? And as I move out with the ramp filter, that cone that's missing gets bigger, but the volume that I'm enclosing in my Fourier space goes up as rho cubed. Right? And so these are the considerations when you're deciding how to design the system, how to run the system. And then when you're testing signal to noise, you can use a phantom, such as this, where you have a specific percent contrast in a row and a change in diameter of the object, and ask the question as, suppose we use a lower and lower number of photons. So the percent contrast stays the same as we go here, but the contrast to noise goes down, right? Because we're using the lower and lower number of photons. And you can basically just observe where the cutoffs occur. You say, okay, at such and such a diameter, with this contrast, I can still see it. However, by the time I get to this contrast, that diameter is no longer a visible object, right? So statistically speaking, if I looked at it and said, is that an object or not? I could flip a coin, right? Because the sample or the value just doesn't reliably give you evidence it's an object there. This is called a contrast detail curve, and it is, I think, particular to CT. I think this is used in CT. I'm not sure it's used in any other medical imaging modality. Okay, that's that. So we got about 20 minutes. Are there any questions to this point? No? All right. I would like to just go through a couple of examples here of the MATLAB functions that are in the modules section with the lectures. And one of them you'll use for problem set 3. And so problem set 3 is really basically just changing parameters in these MATLAB functions and describing what happens, right? And quantifying what happens. And okay, let's try this one first. Okay, so as you've if you've started running these, I hope you have. I put these chunks of code together such that you can change a parameter, just rerun the whole thing, and all of the plots come back up, and you can see how things changed, right? And if you go to the windows, it will tell you what each plot is, right? So for this one, we have the original image. And in this case, the original image are these tiny dots, right? So they're like 1 pixel dots, maybe 1 pixel, I don't know. Let me see what they are. Yeah, like 1 pixel dots. And then for each one of those, we're going to look at a run where we take projections every half a degree, and we're going from 0 through 180 in terms of the radon.